Okay, so if U is the solution of IUT equals to minus Laplacian of U, then for U lambda of xt, we have that lambda to the n over 2 U of lambda x comma lambda squared t, okay, is also a solution. So it verifies that the norm of U lambda t of LP is equal to lambda n 1/2 minus 1 over p multiplied by U of lambda squared t LP. Okay, so the norm of U lambda q LQ or LP, LQ in time, LP in space, this will be equal to the integral in R of lambda in Q 1/2 minus 1 over P multiplied by the norm of U lambda squared T Q LP dt. Okay. This will be equal to the integral in R of lambda in Q 1/2 minus 1 P minus 2 lambda norm of U T. Okay, so the lambda square is out, and well, again we have Q and LP now dt, and this will be equal to lambda nq 1/2 minus 1 over p minus 2 the norm u q, but now we'll have once again the norm lq or LP. Okay, so we finally have that the norm of U lambda, okay, this is lambda U sub lambda of well, LQ this LQ or LP, okay, this is equal to, well, lambda and Q, well, let's make something different. Let's put here n multiplied by 1/2 minus 1 over p minus 2 over q, and the norm u lq r l p. Okay, so if there exists an estimation of the type, let's say norm of u lq our LP less than equal than a constant multiplied by u of, let's say, u of 0, okay, and L2. So then, as the norm of u in 0 has to be equal, L2 has to be equal to the u lambda of 0 in L2, then it must be that 2 over q equals to n 1/2 minus 1 over p. So we're asking this to be 0, basically, so that this holds. And this is a condition that we've seen many times in many theorems, which are the conditions that we have, and we call an admissible pair in different dimensions. It depends if n is equal to 1, p less than equal than infinity, n equal to 2, p less than infinity, n equals to 3, p less than 2n over n over 2, and then we have this. And now we know where it comes from. So our proposition, if p and q is an admissible pair, now that satisfies the condition that we just seen, then exists C positive such that for u naught in L2 of, in this case, we are in Rn, then we have that the norm u of q 0t LP is less than equal than C norm of u naught L2. Okay, and we can see here in this case that ut is equal to wt u naught, and recall always wt is the unitary of operators. Okay, so if p and q is an admissible pair, then we will say the dual admissible pair will be the one that in this case 1 over p plus 1 over p prime is equal to 1, and 1 over q plus 1 over q prime is equal to 1. So if p and q is an admissible pair, and let's say r and gamma it's a dual admissible pair, then exists C positive such that for f and L gamma of 0t and LR Rn we have that the norm of G LQ 0t LP is less than equal than CF L gamma 0t LR. Okay, so you can see Q and gamma and P on R, all the respective duals. G is the integral 0t wt minus s multiplied by f. of S. Okay, so I'll let function b that goes from the complex numbers to the complex numbers that verifies that b in 0 is equal to 0, and that bu minus bb absolute value is less than equal than c1 plus absolute value of u alpha minus 1 plus absolute value of b alpha minus 1 all multiplied by the absolute value of u minus b with alpha greater than 1. Okay, so if q is greater than alpha, okay, then the application, let's say u that goes to bu, satisfies the norm of bu in L1 0t L2 is less than equal than c t norm of u, let's say xt, t1 minus alpha over q norm of u in xt. Okay, and also the difference bu minus bb again in L1 0t L2 will be less than equal, then again a constant, but this time will depend of t of u in xt and p in xt. I will say what is xt, then multiply by t1 minus alpha over q the norm u minus b norm xt. Okay, and where xt is let's say c in 0t comma L2 Rn intersection LQ in time 0t and L2 alpha Rn. I will see after why it appears this L2 alpha. Okay, so remark, if PQ is admissible pair and P is equal to 2 alpha, then Q is equal to 4 alpha over n alpha minus 1. So Q will be greater than alpha, okay, if alpha is between 1 and 1 plus 4 over n. We've seen a lot of times this, that separates always the subcritical case from the critical case.